So the next thing we're going to do in terms of thinking about light as a wave is think about how light reflects and refracts. And so for starters, where does light reflect or refract? And the key thing is that we've got some surface, so there's some boundary between two media. Now this could be air over here and glass over here, or air and water, or glass and water, or it doesn't matter. But the important thing is that there's some surface separating medium number one and medium number two. Now, each of these medium, or both of these media, have property that defines them known as the index of refraction. And the index of refraction is basically trying to tell you something about how much light has to slow down as it travels through this material. So we know that the speed of light in vacuum is c. Whatever the speed of light is in this substance has some velocity value v, and the index of refraction is the ratio of those two speeds. So there'll be some, for medium 1, there'll be the speed of light c divided by the speed at which light travels through this medium. The index of refraction for medium 2 will be the speed of light c divided by the speed at which light travels in medium 2. So this ratio of how fast light travels in vacuum versus in the medium is defining the index of refraction. And so a couple things. One is, well, this means that the index of refraction for vacuum is by definition 1, because that's just going to be c over c. And it's got to be greater than 1 for all other materials. So, say for air, that the index of refraction for air happens to be 1 point, basically 0.0003. So we're going to treat the index of refraction for air as 1. It's not quite, but it's close enough for our purposes. But for anything else, because light always travels more slowly in the medium than it does in vacuum, the index of refraction will always be greater than 1. So for air, it's just barely greater than 1, and so we're going to treat it as if the index of refraction for air was 1. And anything else is going to have some higher value, right? So 1.3, 1.4, 1.5, right? So index of refractions are going to be values greater than 1. So what happens when light goes from one medium to another? And the important idea here is that when it goes from a medium with a smaller index of refraction to a larger index of refraction, so if it's going into a medium with a larger n, then it's going to move at a slower speed. So let's say medium 1 happens to be air, and medium 2 happens to be water. And the index of refraction over here is basically 1. The index of refraction here is larger, 1.3. So when the light ray goes from air into water, it actually slows down. It travels more slowly. Now the number of waves arriving at the surface has got to be the same as the number of waves leaving the surface, right? You don't end up with this light building up at the surface. So that tells us that the frequency doesn't change. So I know that if my light is traveling at a slower speed, but the frequency is still the same, that tells me that it has to have a shorter wavelength. So the wavelength of the light in any material is less than the wavelength of what it is in vacuum, simply because it's traveling at a slower speed with the same frequency. And so we can calculate what the wavelength of light is within some other medium, and it's going to be so lambda naught here is the wavelength in vacuum divided by the index of refraction. So clearly the larger you make the index of refraction, the more you're changing what that wavelength is as it travels through the medium. So one of the things when we're talking about light going from one medium to another, the first thing we're going to care about is what's the normal to that surface. So we'll see here in a minute that all these angles are going to be defined relative to the normal. So we're going to care about the normal. And the normal is just our fancy way of saying I want a line that's perpendicular to the surface. So here my surface is up and down, so the normal to that surface points horizontally. So if we send an incoming ray into the surface, so let's say we've got some ray starting in medium 1 and it's coming into our surface. And the first thing to point out is we will use incoming and incident interchangeably. They both mean the same thing. We're just telling you about the ray as it comes into the surface. And then what happens once it hits the surface? Well, basically it's going to split into two parts. There's going to be a transmitted piece. So there'll be a transmitted ray that goes through into the second medium. So it's going to go through the surface. There will be a reflected piece that bounces back. So your incoming ray will break up into two pieces. A transmitted ray that will go through and a reflected ray that will bounce back at the surface. So let's adjust our picture here. So now here's my surface. So notice I've switched things up so that instead of the surface being vertical and the normal being horizontal, I switched it so that the surface is horizontal and the normal to the surface is now vertical. And so I'm going to let my incoming ray come in at an angle. So here my incident ray is coming in at an angle. And again, it's going to split into those two pieces. So there will be a reflected ray that bounces back at the surface. There will be a refracted ray that goes on through the surface. And so the first thing that I'll point out is there are now three angles that we can define. The incident angle, the reflected angle, and the refracted angle. All of them are defined relative to the normal. So the incident angle is the angle between the incoming ray and the normal. The reflected angle is the angle between the reflected ray and the normal. The refracted angle is the angle between the refracted ray and the normal to the surface. So all three of these angles, it's incredibly critical that we get this because this is an easy way to make mistakes. But all three of these angles are defined relative to the normal to the surface. So for starters, there's a couple rules that we have for how these angles relate to each other. And the first one is the law of reflection. And it simply tells us that the incident angle has got to be equal to the reflected angle. So basically, the way reflection works is that whatever angle your light comes in relative to the surface, the reflected ray is going to bounce back at exactly that same angle. In terms of the transmitted piece, right? So our refracted ray, that's the name for our transmitted piece here. It's going to follow Snell's law. Snell's law is the law of refraction. So when we send something in along the normal, we don't see refraction. But when our incoming ray, our incident ray, doesn't come in along the normal, then we see what's known as refraction. Our transmitted piece is not only goes through the surface, but it also bends relative to the normal. So that's what Snell's law is trying to tell us, is how much will that ray bend, and that's going to depend on what's going on with your two media. So here's Snell's law. Again, Ni and sine theta I is telling you what's going on the incident side. So this is the index of refraction for the incoming ray. So what medium is the incoming ray sitting in? This is the angle it makes with the normal. Nr and sine theta r are the refracted, the index of refraction for the medium that the refracted ray sits in, and the angle, then our refracted angle. So Snell's law basically tells us that Ni sine theta I equals Nr sine theta r. We'll often write these in terms of ones and twos, so we'll often play with these indices, but the way I've written them here is just trying to emphasize that there's a incident side and a refracted side because we have a incoming and transmitted ray, and we need to make sure that our indices of refraction and angles match up. Now, if you go through and do the math, so here's our incident angle, again defined relative to normal. Here's our refracted angle, defined relative to the normal. And if you go through and do the math, if it works out that the index of refraction for medium 2 is larger than the index of refraction for medium 1, then your transmitted ray, this refracted ray, is going to bend towards the normal because the light is going to move more slowly over here than it does over there. It's going to move more slowly in medium 1 than it does in medium, or more slowly in medium 2 than it does in medium 1. Come in. So if, on the other hand, my incoming ray is in a medium where the index of refraction is greater than what it is for the refracted ray. So here's a situation where in 1 is greater than in 2. Then what I see is that the refracted ray will actually bend away from the normal, because now it's speeding up. And so the sort of heuristic that we'll end up using is thinking about, well, if it goes from lower index to higher index, the refracted ray will bend towards the normal. If it goes from higher index to lower index, it will bend away from it. So obviously there's a point at which I can make it bend. So if it's going from higher index to lower index, so here's still N1 is greater than N2, I can have an incoming ray that bends so much away from the normal, it's actually going out along the surface. This is a special situation where my incident angle is now known as the critical angle. So that's my theta sub c here, that's the critical angle. My refracted angle is now 90 degrees. And this whole process is known as total internal reflection. So with total internal reflection, what I have is I'm at the critical angle so that the refracted ray, instead of transmitting through, is actually going out along the surface. Which means that when I look at Snell's law, I can solve this for theta c, because sine 90 is just 1, and it tells me that it's easy to calculate the sine of the critical angle is just going to be the ratio of my refracted index, the index in the medium where my refracted ray is trying to go, divided by the index for the incoming ray. Since the incoming ray is sitting in the higher medium, this ratio is always less than 1, which it has to be for my sine theta to make sense. So this is why total internal reflection only occurs if my incoming ray is sitting in a higher index of refraction than the medium it's trying to go into. So if I switch over so that my incident angle is larger than the critical angle, then what I actually get, and here's the total internal reflection part, is that nothing is transmitted. Everything is reflected back. And so this is actually a way to get great reflection with very little loss in the light. And we'll talk about some situations where we take advantage of and use total internal reflection, because I can keep my signal moving in some sense without losing any of it, because all of it gets reflected back based on the physics between these two media. And so these are the properties of reflection and refraction that we'll end up dealing with as we talk about light going between one medium and another.